Hi, in this video, we're going to cover a couple of examples on recursion that are based on problems out there someplace. Anyway, the first one we're going to do is called towers and has to deal with towers of Hanoi. It's a legend that in Hanoi, there's a monastery and God brought down three golden towers, and on one of the towers were 64 discs. Each disc was a little bit smaller than the one below it. The task was to move all the discs from one tower to another using the third tower as a temporary holding place with a couple of stipulations. One was that they could only move one disc at a time and they could never put a larger disc on top of a smaller disc. Now, as the theory goes, that in order to do this, it would take billions of years to complete it, and then when it's completed, that would be the end of the world. But that's, like I said, a legend on there. So what we're going to do is we're going to write a program that will give you what the moves are if you without making any mistakes. So let me start up a blank file, or a new file here. So we're going to create a function here. We're going to pass in the height, the from pole, the to pole, and the width pole. Okay, so now when you work on this, if you had a display, and long time ago, my dad made me a representation of this with 5 discs that I could use on here. But when you go to move these, if you don't make any mistakes, it takes 2 to the n, where n being the number of discs, minus 1 moves. So small, it's not bad. If it's 3 discs, 2 to the third power is 8, minus 1 is 7. If it's 4, it's 2 to the fourth power, which is 16, minus 1, which is 15. If it's 5, that's 31 moves. 2 to the fifth power is 32 minus 1. Think about it if it was 2 to the 64th power minus 1. Use a calculator and see if you can come up with an answer on that one. So in here we want to do if our height is greater than or equal to 1, then we're going to call move tower, passing in the height minus 1, height minus 1, the from pole, the width pole, and the to pole. Notice that the order of the poles are different, and we decrease our height by 1. We then call move disk, passing in the from pole and the to pole. Okay, so the order that they go is important on each of these. Then we call move tower again, passing in height minus 1, the width pole, the to pole, and the from pole. So remember that when we do this, the discs are going to be moved, so there's going to be discs on different poles as we do this, and so where we get the pole from and where we're moving it to changes on here. Okay, so we're going to need a method or a function for the move disk, and the from pole, and the to pole. So we're just going to print out a message here showing this. Moving disk from percent %d to %d. And we're moving FP and 2P. Create a main here. We'll call move tower, passing in 4 is the number of discs, pull 1, pull 2, and pull 3. Okay, so let's get this saved. And I'm just going to call it tower.py and go to the location where I want to put this. Whoops, wrong place. Let's back out here so I get to the right location here. There we go, that's the place there. Okay, get that saved. And we'll run this. And there's the move for 4 disks. Like I said, if you count those, there's 15 of those, 2 to the 4th power minus 1. Okay, so you have to move the first disk from 1 to 3, move the next disk from 1 to 2, because you can't put it on top of 3. Next disk from 3 to 2, and then down through there on getting them all moved. Okay, so if we made this, let's go up 2 numbers on this. I'm going to go up to 6, because 5 I already told you was 31. 6, and there's the moves that you need to do in order to get that to work. And eventually, when you get up pretty high, 10, 11, 12, even up to probably 8 or 9, it gets a lot of moves in here. Okay, so see how fast it runs though doing that. Okay, so let's do the next example. Open up a new file here, and if any of you have heard about what Fibonacci numbers are, Fibonacci numbers are a pattern. I'm going to put it up here so you can see it. So the pattern is that you take the 2 previous numbers and add them together, and that makes the next number. So we start with 1. The previous 2 numbers, there's only 1, so it's 1. Previous 2 numbers are 2, so that's the next one there. Previous 2 numbers, 2, 1 is the 3, 3, 2 is the 5, 5, 3 is the 8, 8, 5 is 13, and so on. That's the pattern. So what we want to do is write a program that will recursively find the next sequence. We're going to do this using time, so you can see how much time it takes to do this. Okay, so we're going to import time and call it fib, passing in n. So if n equals 1, we're going to return 1. Else, oh, I'm sorry, not an else. If n equals 2, we're going to return 1, 1. Then we're going to set fibs equal to 1, 1. And then for I in range 2, n, fibs dot append fibs minus 1 plus fibs minus 2. And then when we get done with that, we're going to return fibs. Okay. So for n in range 1 to 1000, start our time. Start equals time dot time. We're going to call fib n, and then we're going to print n time dot time minus start, and then we'll call main down here. Okay, so this is going to print out the value n and then what the time was to do that. Okay, so if you look at this, this should be an on, and that is because these two and the return are don't mean anything. Actually, those two, the fibs here and the return, don't mean anything. They're inconsequential on this, insignificant. The for loop is the only one, and the for loop is running n times, actually n minus 2 times, but it's running n times. And so as n gets bigger, the for loop runs n number of times on there. So we're going to go ahead and I'm going to get this saved. I don't want to do that. I'm going to save this as fib no recursion.py. And then we're going to run this. Notice how the time has not changed on any of these. A little bit every once in a while you get a flicker in there where it is a couple of seconds or a couple of tenths of a second or hundredths of a second because of the computer doing something. We do this for 1,000 of these. To 999, 0 to 999. And notice these are the only ones in here, hundredths of a second. And that's just because there's probably something on the system that glitched at that point. Okay, so let's see what happens when we create or do this recursively. So again, we're going to import time. And we're going to create a function called fib passing in n. So this time, if n equals 0, then we're going to return 0. Else if n equals 1, we're going to return 1. Else, we're going to return fib n minus 1 plus fib n minus 2. Okay, because n is the value that was just prior to n and the value that's 2 prior to n. Okay. So do our main. We're going to set n equal to, let's do 10, start with. For I in range 1, comma n plus 1. Start equals time dot time fib I, end equals time dot time. And they're going to print I and end minus start. Okay, let me save this one. Oops. And I'm going to save this one as fib recursive. Oops, got an error in there. Must have missed my equal sign. Oops. Okay, no times on there, okay? Ran it 10 times. Let's change 10 to 20. Oh, starting to get some time in there. Let's change 10 or 20 to 25. A little bit more time, got up to 5 hundredths of a second. Okay, let's go to 30. Oh, starting to take a little bit longer now, up to 5/10 of a second for 30. 31's taking a little bit, oh, that was all of them, okay, 5/10 of a second. Now we're going to go up to 40. and see what happens here. Okay, we're up to a second now, 2 seconds. Okay, it's like almost doubling. When you're waiting for something, seconds seems like a long time. So that's almost 16 seconds there for 37. Next one here is probably going to be close to 30. Taking quite a while. There we go. Well, 25. 2 more to go. Get 39 done, then I'll go back and talk about the program, while we wait for a 40. It's going to be more like a minute, so close to 50, 45, 50 seconds, I'm guessing. 41. Okay. So let's look at the program here, and then we'll come back over there. So what's happening here is every time fib is called and the number is not 0 or 1, then it calls fib again twice, passing in n minus 1 and then n minus 2. So when this happens, when you do 40, right, you got to think about it's 2 to the n power just about on doing this, because when n is 40, then it calls 39 and 38. Then this one, which is 39, has to call 38 and 37, and then that one has to call 37 and 36, and then all the way down that way, and then this one has to go all the way down this one, and each one of those splits off 2. So you can see how many are on there. Still hasn't completed for the 40 yet. So that shows you that sometimes recursion is not the best option for doing something, especially something like this where you have as you get the numbers really large, the time really goes out. Remember that on the one that we just did, I think I close it. No, this one here. For this one here, that it was not recursive, we did 1,000 times, and it never got a time. Well, a few of those 0.001s, but never increased on time because it's 1. So there's 72 seconds on 40. That's over a minute. Doesn't seem like a lot of time here, but what if you needed to do 100? Just think how much larger that would be on there. So that's just something to think about when you're working with recursion, that something may look like it would be a lot better with recursion. Okay, so you have this one here. You think, oh yeah, I got those two, two if statements there. We got this for loop that's got to run in here, and a little bit more code and everything. Maybe going recursion would be a little bit better, make it a little bit slicker. But let me move this over here. There we go. But the recursion takes a lot more time if you have a lot of numbers. So just something to think about. So I hope you enjoyed the video and you got something out of it. Bye.